Hello and welcome to the solutions video for our Unit 5 unit exam. So our first question, we have a pilot flying her airplane at a constant speed in a vertical loop-to-loop. And we have some free body diagrams to pick from. At the position shown, her acceleration is. Well, if you're going in a circle, the acceleration is always pointed to the center. So it must be to the left. In which row below shows the free body diagram that would be most appropriate for the pilot at the top of the loop, and which is most appropriate at the bottom? Well, at the top, then everything would be pointing downward, so that's diagram 4. And at the bottom we have gravity still pulling down, but the net force still has to be center, which is up. So that would have to be diagram 2. Remember, these vector arrows are proportional. Our written response. We've got a marble that is rolled down a track and into a vertical loop with a diameter of 42 centimeters. At the top of the loop, the track exerts a downward force on the marble equal to the marble's weight. Okay, so what is the speed of the marble at the top of the loop? All right, so we have this loop here. Track is exerting a force equal to the marble's weight. So mv squared over r is mg. We cancel our masses, and v is root gr. So that is 9.81 meters per second squared. Our r is 0.21 meters because it's half of our 42 centimeter diameter. So if I run this through the calculator, the square root of 9.81 times 0.21 to the correct sig digs, it's 1.4 meters per second. So I'll just pop into the other window here, mark that written response. All right. So now, a satellite in low Earth orbit has a mass of 1.88 times 10 to the 3 kilos and orbits a distance of 7.59 times 10 to the 3 kilograms from the center of the Earth. Now we have to figure out how many hours it will take to orbit the Earth once. So here we have our centripetal force equals our gravitational force. These masses cancel. But we're asked for how many hours, so we have to turn our v squared into 4 pi squared r squared over t squared. That's times 1 over r equals gm over r squared. So here's our relationship, which still needs to be simplified. We are just looking for period. So we have 4 pi squared r cubed is gmt squared. So period is 4 pi squared r cubed over gm. I should point out, I should have actually pointed it out on the last question, some of you were just memorizing equations like the conservation of energy, and that fouled you up on this one because it wasn't done with conservation of energy. It was a different relationship. So just rote memorization of solutions means nothing if you don't understand the solution that represents. This is why I encourage you to rederive each time, because then you have to think what is actually happening in this case. So The formulas that are on the formula sheet are the ones you should start with, and don't use rote memorization for things that are not on the formula sheet. Anyway, 7.59 times 10 to the 6 meters here. It said 10 to the 3, but that's in kilometers, and we want it in meters to get it down to our seconds for our period. G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And the mass here is 5.97 times 10 to the 24 kilograms. That's the mass of the Earth on our formula sheet. So going to the calculator, 4 pi squared times 7.59 E3, or no, sorry, E6 cubed divided by 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. We take the square root of that, and we get 6,584 seconds. But at 60 seconds per minute and 60 minutes per hour, we divide this by 3,600, and we get 1.83 hours. All right, so we have our orbital radius and our orbital periods. So we've got 5 planets that have been identified with the orbital radii and periods listed below. We want to find the mass of the star. So this is going to be using that full version of Kepler's third law that we derived above. So if we've derived it here, we can use that same derivation. And we want to get m. We want our mass out of this. So ideally, our mass is our slope. So we need one variable on one side. We'll keep the r cubed here. We'll pull out our mass as our slope. And that leaves us with gt squared over 4 pi squared. This is our horizontal variable. So the other option here, we've got everything on the left, I see. So that is going to leave, if we have just the versus t squared, right? That's the only version that has an r cubed on one side and the t squared on the other. So this has to be our linearization because it's the only one that represents it. So with this multiple choice answer key, here is our y, and t squared is our x. So now to actually do this regression and get our mass, we are given the orbital radii. So here's r, here's t. So we have 2.58 E7. Just going to move that tab closer. 1.02 E8. 3.10 E8. 5.09 E8. And 2.91 E9. Now our period is 1.66 E5, 1.36 E6, 7.21 E6. Of course, with your calculators, I don't have the calculator at home to report the solution, but in this case we'd want to be typing in the t squared directly in our y column, or sorry, in our x column, So our modified y and our modified x. Yeah, so here it is this squared. We'll fill down. And now our y is 4 times pi squared times r cubed. That's our numerator, and our denominator is 6.67 times 10 to the negative 11. So again, instead of taking the time to type these in on the calculators, we'd have typed them in here in their adjusted forms. So that's our 4 pi squared r cubed over g and our t squared. And now this wants the y's first, then the x's. So there's our slope, 3.61 times 10. This is saying 23. Oh, you know what? Our orbital radii, that was in kilometers. So I need to convert that to meters. There we go, 3.61 times 10 to the 32. That's why it was off by 10 to the 9. So 3.61 times 10 to the 32 kilograms. So now a pulsar, it's a very dense kind of star, has a diameter of 30 kilometers and rotates once every 1.8 milliseconds. Now, I can't tell you what milli means in the test, but if you explore your formula sheet, you will find it is labeled as 10 to the negative 3 there. So an object at the pulsar's equator would have a centripetal acceleration of a given magnitude. So the centripetal acceleration is just v squared over r. We don't need that one, we'll come back here. Or 4 pi squared, and r, we're going to be dividing by r, so that r cancels. This is our centripetal acceleration. So we have a radius of 30 kilometers and a period of 1.8 milliseconds. So you'll notice I'm not trying to move the decimals too much when I'm converting things. I'm just adding 30 times 10 to the 3. It's not proper scientific notation, but it is a more reliable way to enter the numbers into your calculator. Oh, and I did, yes, that's a diameter. One of the side effects of recording these videos at 5:30 a.m. is that sometimes you miss silly little things. Okay. So there we go. It works out to our two significant digits from time, 1.88 times 10 to the 11 meters per second squared. So 1.811. And if this is coming from gravity, then that means the acceleration we just got, right, is equal to that gm over r squared. So, and we have ACR squared over G. So it's the 1.8 with all the digits we see on our calculator, times our radius of 15 times 10 to the 3 meters. Doing that correctly this time, instead of forgetting to convert the diameter. So this times 15 times 10 to the 3 squared divided by g, and it's 6.1654 or 6.2 times 10 to the 29 kilograms. All right. So next up, we have to align these with Newton's law of universal gravitation, Kepler's first law, Kepler's second law, and Kepler's third law. So, sum of these four. The area swept up by a planet in its motion on the sun is equal for equal time periods. That is Kepler's second law. So 4 goes in this spot. We know that planets travel in elliptical orbits around the sun with the sun at one focus is Kepler's first law. Kepler's third law is about the ratio of the orbital periods squared, and the average orbital rest cubed is the same for any two objects orbiting the same mass. So that leaves number one, or sorry, statement. Right, okay. That one is Kepler's third law. I had that in the wrong spot. So yes, this is a 2 for, number 2 is Newton's law of universal gravitation, which is that the planets travel fastest when they're at the closest approach to the sun and the slowest at the further approach. That is not explicitly Kepler's third law, or Kepler's second law. Kepler's second law is explicitly number 4. They are connected, but that's because we use Newton's third law of motion to explain that. So that was the challenge in that set. So now, a 300-gram ball is swinging in a vertical circle at the end of a 1.2 meter string. The speed of the ball at the bottom of the swing is 8.5 meters per second. The minimum speed needed at the top of the circle. The minimum speed is always when the force of gravity equals the tension. Or sorry, the force of gravity equals the centripetal force, and tension is 0. So we are back to our root GR. Which is 3.43 meters per second in this case. So we have the speed at the bottom, and if we do conservation of energy, we may or may not get the 3.43 number, because they're now asking for the minimum speed. So you're allowed to change the speed at the bottom to hit that minimum at the top. So that's why we can't just use the straight conservation of energy that we used for similar problems. It's because that word minimum there changes the situation. So we'll see how we did, and we did well. Oh, and the outcomes are a side effect of the fact that I didn't update them after building this as part of the final exam. But yes, these are the solutions to the test.